Today, I will discuss Bohr's model of atom in this tutorial. Let's start with introduction. This model was proposed by Niels Bohr. This model is based on both classical and quantum theory of Planck. The important postulates of this model are: the first postulate gives the idea about circular orbits. An electron can revolve only in those orbits whose angular momentum, mvr, is an integral multiple of h by 2 pi, that is mvr equal to nh by 2 pi. Where m is mass of electron, v is velocity of electron, r is radius of orbit, h is Planck's constant, n is number of orbit in which electron is present. The electrons revolve in particular orbit, it neither gains nor loses energy during revolving. So, the circular orbit is also known as stationary orbit or energy level. When electron jumps from one orbit to another, the difference in energy is emitted as radiation given by delta E equal to E2 minus E1 equal to HV. When electron jumps from lower energy level to higher energy level, it gains energy, but when electron jumps from higher energy level to lower energy level, it loses energy. These are the postulates of Bohr's atomic model. Advantages of Bohr's model of atom. The experimental value of radii and energies in hydrogen atom are in good agreement with that calculated on the basis of Bohr's theory. Radius, r, is equal to n square h square by 4 mu square me square z. Or, r is equal to 0.529 into n square by z Armstrong. Where 0.529 is the radius of the first orbit of hydrogen atom. Bohr's theory satisfactorily explains the velocity of electron in an orbit. V is equal to 2 pi e square by nh. The velocity of electron in the first orbit, that is when n is equal to 1, is also known as Bohr's velocity. Its value is v1 is equal to 2.19 into 10 to the power 8 cm per second, which is 1 by 138 of velocity of light. That means Vn is equal to 1 by 138, n of velocity of light. By using this formula we can calculate velocity of an atom in any n orbit. Bohr's theory satisfactorily explains the energy of electron in an orbit. En is equal to minus 2 pi square mz square e to the power 4 by n square h square. That means En is equal to minus 13.6 by n square eV. From these relations we can say energy of an electron is directly proportional to the square of n. Although the energy of an electron increases with increase in the value of n orbit, yet the difference of energy between successive orbits decreases. Thus, E2 minus E1 is greater than E3 minus E2 is greater than E4 minus E3 and so on. Bohr's model could also explain the hydrogen spectra with following spectral lines: Lyman series, Balmer series, Paschen series, Brackett series, Pfund series, Lyman series. If the transition of electron takes place from any higher orbit to first orbit, we get Lyman series of the hydrogen atom. It is obtained in the ultraviolet region. Balmer series. If the transition of electron takes place from any higher orbit to second orbit, we get Balmer series of the hydrogen atom. It is obtained in the visible region. Paschen series. If the transition of electron takes place from any higher orbit to third orbit, we get Paschen series of the hydrogen atom. It is obtained in the infrared region. Brackett series. If the transition of electron takes place from any higher orbit to fourth orbit, we get Brackett series of the hydrogen atom. It is obtained in the far infrared region. Pfund series. If the transition of electron takes place from any higher orbit to fifth orbit, we get Pfund series of the hydrogen atom. It is obtained in the far infrared region. This is details figure showing Lyman series, Balmer series, Paschen series, and Brackett series. You can see it also. In summary, the advantages of Bohr's model of atom are: Bohr's theory satisfactorily explains the spectra of species having one electron. The experimental value of radii and energies in hydrogen atom are in good agreement with that calculated on the basis of Bohr's theory. Bohr's concept of stationary state of electron explains the emission and absorption spectra of hydrogen-like atoms. The experimental values of the spectral lines of the hydrogen spectrum are in close agreement with that calculated by Bohr's theory. Limitations of Bohr's model of atom. Bohr's model of an atom failed to explain the Zeeman effect, the effect of magnetic field on the spectra of atoms. It also failed to explain the Stark effect, the effect of electric field on the spectra of atoms. It also violates the Heisenberg uncertainty principle. It could not explain the spectra obtained from larger atoms.